So hello everyone, I'm Qianchen Xu from Unity Research Center. So just imagine that you are walking on a very busy street, and there are some people who move in the same direction with you, and also others who move in the different direction with you. So in order to move faster to your direction, you will choose to follow the person who move in the same direction with you. So therefore, people who move in the same direction form names in this situation. And this phenomenon is called name formation. And today I will introduce the relationship between the anticipation and the name formation with the help of simulations. So my talk has 6 parts. The first part is a model structure. And to model the movement of pedestrians, we need to define a method to calculate the velocity of the pedestrian. So in this talk, all the model I used has the same structure, where the direction of movement and the speed are calculated by 2 submodels separately. So we start from the submodel for direction first. For each agent, we define a desired direction for this agent and toward its target. Then we calculate the influence from neighbors. And finally, combining the desired direction and the influence from neighbors, we can get the direction of movement for this agent. Then we go to the submodel for speed. So for each agent, its speed is determined by its free speed and the distance in front. So this animation shows the relationship between the speed and the distance in front. And also, this relationship is plotted in the bottom right figure. So in this figure, the x-axis is the distance, and the y-axis is the speed. And the parameter t here is used to adjust the slope of the relationship. So actually, I left a question when I introduced the submodel for direction, because I didn't introduce how to calculate the influence from neighbors. And in this talk, I will introduce 3 different methods to calculate the influence from neighbors. And these 3 methods are from 3 different models. And in the first model is called collision-free speed model. So this animation shows the influence from the blue agent to the red agent. The direction is always from the blue agent to the red agent. And the strength of the influence is an exponential function of the distance between these 2 agents. So this relationship is also plotted in the bottom right figure. And in this figure, the x-axis is the distance, and the y-axis is the strength of the influence. And the second model is called generalized collision-free velocity model. So from the name, you can know that this model is an extension of the first one. And in this model, we still use the exponential function to calculate the strength of the influence. So which means we use the same relationship here, shown in this figure. But for the direction of the influence, is determined by the relative position of the blue agent and the desired direction of the red agent. So which means this direction is always perpendicular to the desired direction of the red one. And the last model is called anticipation velocity model. So we still use the same method as the last one to calculate the direction of the influence. But for the strength of the influence, we will introduce anticipation by considering the future positions with this process. And therefore, to calculate the strength of the influence, we will use the predicted distance between 2 agents instead of the actual distance between them. Before comparing these 3 models in bidirectional node simulations, I will start from the interaction between 2 agents. So I will consider 3 scenarios. The first one is a fast agent moves behind a slow one. And the second one is 2 agents with the same speed move toward each other. And the last one is 2 agents move across each other's path. So this is the result of the first scenario. So in model 2 and model 3, the fast agent just overtake the slow one. And with the anticipation, this overtake appears earlier in model 3 than model 2. And now is the result of the scenario 2. So also in model 2 and model 3, these two agents avoid each other. And also with anticipation, this avoidance happens earlier. And the last scenario, we can only see the cross path in model 3. These two agents cross each other and move to their target. Okay, and finally we come to the bidirectional flow simulations. So we will run simulation. We already ran simulations in a corridor shown in this figure. So two groups of agents with the same number are distributed in the two waiting areas and move toward each other. And periodic boundary conditions are used in our simulations. And here is the result of the bidirectional flow simulations. So in model 3, land formation appears very early in the simulation. So agents just form lanes very quickly. And in model 2, the two groups of agents fall into gridlock in the mid of the corridor. And in model 1, it will take some time to see the land formation in this simulation. So we just wait here for a moment to see the land formation appears. It will take some time. So we see the land formation in this simulation now, and we can move on. Yeah, so to compare these three models quantitatively, first I just compare the jamming probability in the simulation. So for each model, I run simulations in different densities, and for each density, I just arrange simulation for 30 times with different initial conditions, and to see how many simulations will be in gridlock, and then we calculate the jamming probability according to this function. So the result of the jamming probability is shown in this figure. The x-axis is the density, and the y-axis is the jamming probability. So model 3, the jamming probability in model 3 is much lower than other two models, especially in the high density areas. And then to identify land formation in the simulation, I use the order parameter. So the order parameter of each agent is calculated according to this function. And in this function, n-same means for each agent, n-same means the number of agents who move in the same lane and also in the same direction with this agent. And n-differ means the number of agents who moves in the same lane but in the different direction with this agent. So the higher the value of, the higher the order parameter means the stronger the land formation in the simulation. So the result is shown in this figure. The x-axis is still the density, and the y-axis is the order parameter. So in model 3, the order parameter is always closer to 1, which means a very strong land formation in the simulation. So, and also this value is much higher than other two models. The last quantity I used is the land formation time. So it's defined as the first time when the value of order parameter is higher than 0.8. And also the result is shown in the figure. The x-axis is still the density, and the y-axis is the land formation time. So in model 3, net formation appears much earlier than other two models. Since model 3 works well in bidirectional scenarios, so I use the experimental data to validate this model. So first, I calibrate the model with the fundamental diagram from bidirectional flow experiment. The left figure shows the relationship between the speed and the density, and the right one shows the specific flow and the density. So after adjusting the parameters of the model, the result obtained from simulation fits well with the experimental data. And then I ran simulations with this model in unidirectional flow scenarios. And I found this model can reproduce the difference between the fundamental diagram of uni and bidirectional flow scenarios. So this difference is already observed in the experiment, so which is shown in the left figure. And the simulation result is shown in the right figure. They are both the relationship between the specific flow and the density. So we can say actually the model can reproduce pretty well the difference between these two different scenarios. Introducing anticipation into the model can really improve the performance of the model in bidirectional flow scenarios, but it's still not enough for more complex scenarios. So in the future, I'm going to implement models in this structure, which means agents can choose their strategies to move according to their perception and prediction of the environment. So here is an example. After introducing the strategy of pushing others, agents can move pretty well in the crossing scenarios. Okay, so that's all of my talk. Thank you for your listening. If I have any questions, please contact me through this email. Thank you.